Hi, this is Leah from OpenIntro. In this video, we will see how to carry out a hypothesis test and a confidence interval for paired numerical data. In the early 1990s, researchers in the UK collected data on traffic flow, number of shoppers, and traffic accident-related emergency room admissions on Friday the 13th and the previous Friday the 6th. The distribution of traffic accident-related emergency room admissions for 6 such pairs of dates, along with the summary statistics, are shown below. A. Conduct a hypothesis test to evaluate if there is a difference between the average number of traffic accident-related emergency room admissions between Friday the 6th and Friday the 13th. So, in order to structure our response, we'll use this familiar I4C framework: identify, choose, check, calculate, and conclude. So first we want to identify the hypotheses, and we'll test those at the alpha is 5% significance level. So first we want to observe that we have paired numerical data. And so these two groups, the data for the 6th and the data for the 13th, are not independent of each other. They are paired by year. And so we have the summary statistics for each one, as well as the summary statistics for the difference. And what we're really interested in here is testing about the difference. And so our null claim is that the mean of the differences is 0, which is to say that on average, they're the same. And so we'll define the order in which we're taking the difference as the 6th minus the 13th. It's important to specify what order you're taking this so we know how to interpret the results. Our alternate claim is going to say that this mu sub diff is not equal to 0, which is to say that on average, there is a difference in the traffic-related emergency room admissions. So which test will we do? We're looking at differences, and we'll be looking at a mean of those. So we're going to do the familiar one sample t-test for a mean. So this test is a one sample t-test for a mean, as you've probably seen before, but here we'll carry it out on a list of paired differences. And now check the conditions. The conditions are the same as for a one sample t-test, but on the differences. So we need a random sample of differences, or differences generated by a matched pairs experiment. And here we will have to assume that the 6 years are like a random sample. So our results will depend upon this assumption. For the sample size, we have 6 as our sample size. That's the number of differences. So that's not at least 30. So we'll look at the we'll look at the probability plot. So the normal probability plot we can see is kind of linear, and so the distribution of sample differences is approximately symmetric. So we'll assume the distribution of population differences is nearly normal. Next, we'll calculate the test statistic. T is the point estimate minus the null value divided by the standard error of the estimate. And this has n minus 1 degrees of freedom. So our point estimate for the true mean difference is the sample mean difference, and that is given as negative 3.33. The null value is what we hypothesize under H sub O, and that's 0. Here we have the sample standard deviation, and that's given as 3.01, and then the sample size, the number of differences, is 6. So we plug that in and we get our T test statistic. We can see that the degrees of freedom is 6 minus 1, which is 5. Okay, so now we can calculate the T test statistic and the p-value. You can evaluate it as is. Here we have a two-sided test, so the p-value will correspond to the area in the upper and the lower tail. We'll have to add those up, the upper and the lower tail, because we have a not equals to here. So we have a two-sided test. For a shortcut, we can grab a calculator. I'm going to use a TI here and go to Stat, Tests, T-Test. We're doing a T-test. We don't have all the data. We have the summary stats. Our mu sub 0 is 0. That's what we're hypothesizing for mu under H sub O. Our sample average is negative 3.33. Our sample standard deviation is 3.01. And our sample size is 6. Our alternate hypothesis is two-sided, not equal to. And now we'll calculate, and we get our t statistic, and immediately below that our p-value. So we can record those values. And now we're ready for our conclusion. Our p-value is less than our significance level. It's less than the alpha of 0.05. And so because of that, we reject H sub O. And if we reject H sub O, we have evidence for H sub A. So here we're saying we have evidence that, on average, there's a difference in the number of traffic accident-related emergency room admissions between Friday the 6th and Friday the 13th. Okay, now let's do a similar thing, but for a confidence interval. So now, instead of testing a specific value, we want to find an interval of all reasonable values for the mean difference. So we'll use the same framework here: identify, choose, check, calculate, conclude. First, we want to identify what it is that we're trying to estimate and with what confidence level we'll estimate it. So we're going to estimate the true mean, and we'll do the difference in the order 6th minus 13th. So that is the average difference, or the mean difference, between traffic accident-related emergency room admissions on Friday the 6th and Friday the 13th. And we'll estimate this at the 95% confidence level. So similarly, we'll be doing a one sample t interval. And this one sample t interval, we'll be doing it for a mean of paired differences. We've already looked at the conditions. They're the same for the interval as for the test. So we have to make a couple assumptions in order for this test to make sense. We're assuming that the 6 years are like a random sample. And based on our sample data, we're assuming that the distribution of population differences is nearly normal. And we're basing that on assumption on the fact that our normal probability plot is pretty linear. And now we'll calculate the point estimate plus or minus the critical value times the SE of the estimate. The point estimate for this mean of differences is the sample mean difference, plus or minus, in this case, t star. And then the standard error is going to be given by the sample standard deviation divided by square root of n. And so our x bar sub diff is given as negative 3.33. We can plug in the sample standard deviation for the differences of 3.01 and divide by square root of n diff, which is 6. Degrees of freedom is 5, and now we just need to find t star, so we can pull up a t table. Our degrees of freedom is 5, so we'll go to row 5, and we'll look at the column that corresponds to 95% confidence, and we see that our critical value, t star, is 2.571. So 2.571, we'll plug that in for t star. And now we can evaluate this. We can just evaluate it, or if you like, you can use a shortcut here. So instead of going to stat test t-tests, we'll go to stat tests t-interval. So t-interval, we don't have all the data. We're using summary stats. Plug those values in. We've already done that, actually. And so now we can do calculate. And there we get the lower and upper bounds. So we can record those. And now we're ready for our conclusion. We're 95% confident that the true parameter of interest is between this lower and upper bound. So we're saying that we're 95% confident that the true mean difference in traffic accident-related emergency room admissions between Friday the 6th and Friday the 13th is between negative 6.49 and negative 0.17.